Our lovely blue world only has a single moon. It looks battered and sorry for itself. It has clearly been hit a lot of times, smashed into with colossal falsetto, create craters so enormous that we can spot them just by gazing upwards into the night sky. But perhaps this was not a slow siege, not a slow assault by the cosmos on the moon's battered surface. Instead, it was a blitzkrieg. Data on the moon's surface indicate that these collisions might all have occurred within a very cosmologically brief amount of time. An onslaught of plummeting meteorites swept across the moon in an apocalyptic rain. Scientists refer to this event as the late heavy bombardment, and although it is a theory, it would have been a genuinely catastrophic era of history. With some unexpected fallout, it might be the reason we're here today at all. But if it actually occurred, what triggered it? And if the moon was so damaged, why didn't the Earth follow suit? Come with me today as we travel back in time 4 billion years into the past, to unravel a tale of disorder surrounding our newly established sun as its planets calm down into the orbits that we are familiar with today. When the Apollo astronauts returned from the moon, the rocks that accompanied them narrated an unexpected tale. The astronauts had returned with samples filled with impact, melt rocks that had superheated to magma as a result of being struck by a meteorite, which had subsequently cooled slowly back into solid rock. But whereas the Apollo crew had obtained these reconstituted rocks from various regions and craters on the near side of the moon, nearly all of them dated to around 4.1 to 3.8 billion years ago, with significant few exhibiting older impacts. The suggestion, for some reason, during this interval of about 500 million years, there had been an irregular spike in meteorites falling that impacted our moon. This concept became referred to as the late heavy bombardment. This concept is not widely accepted, and not everyone subscribes to the notion that it occurred that way. That is the sort of thing that happens when science is developed on incomplete evidence. We don't get to the moon very usually to go take more samples, so it's difficult to tell whether some process has been contaminating the waters. But if there was a late heavy bombardment, what might have caused it? To find out, we have to look back at conditions around the beginning of our solar system. It is a widely recognized concept that our solar system was created from an accreting disk of intergalactic dust and matter 4.6 billion years ago, orbiting around a gravitational center that would eventually contain the sun. Gravitational perturbations made some of this dust clump together, and once it did, each big ball of matter found itself snowballing in size. Greater clumps had greater gravity, which drew more mass in to expand the clumps. By this time in history, the enormous spinning disk of material from which our entire solar system was formed had clumped together into planetesimals. These then attracted one another, crashing together to form the planets we know today, within a mere 100 million years. This process of planetary accretion had gathered up almost all the material near the sun to form what we call the terrestrial planets: Mercury, Venus, Earth, and Mars. One off these impacts formed our moon, flinging a huge lump of molten rock into space, which formed into a sphere and cooled, and has remained in orbit around our planet ever since. There would still be some isolated leftovers between these planets. Some are still out there today, like the 1.5 million floating asteroids orbiting the sun between Mars and Jupiter. But this process had pretty much cleared out everything in the inner solar system. But under this idea, you might expect to have more impacts at the beginning, but fewer and fewer impacts as time went on, not a sudden spike. So why could there have been a surge in impacts 4.1 billion years ago that gave our moon such a beating? Has left quite a brain teaser for scientists, though some now believe they might have solved it. The finger of blame is pointed at Jupiter, the biggest planet in our solar system with over 2.5 times the combined mass of all the rest of the planets, and the first to condense was Saturn as our solar system began to take shape. If you want to know more about Jupiter and how it affects our solar system, have a look at this video, The Behavior Jupiter is Suspected of, central to explaining the observations which have resulted in the position of the late heavy bombardment. Theory: Jupiter didn't always orbit at a distance of 768 million kilometers from the Sun. Early on, Jupiter traveled inward toward the Sun, hitting about where Mars orbits today. Mars and the other inner planets hadn't yet formed at that point. Then suddenly, turn around and pull away once more. All this perhaps within a few hundreds of thousands to several million years. Why did Jupiter act like this? The shortens worries. Because of its affair with Saturn. When Jupiter coalesced, there was still a massive amount of gas whirling around. Our emerging sun? This gas pulled Jupiter towards the center of newly emerging solar system. After Saturn had emerged, it too joined this death ride, towards the sun. But the two new planets stuck together. As their gravities merged, and the sudden pull of Saturn behind it was sufficient to arrest Jupiter's stately procession toward the inner realm of the solar system, and to softly pull it back to the orbit that we observe it at today. But this procession had not been without effect, literally. Our asteroid belt, with its 1 to 2 million asteroids, possibly only is less than 1% of the material that on sea existed there. And then Jupiter swept in. With its huge, long-reaching gravity, many orbits were disrupted. And a great many of those bodies began to move inward. Two types of asteroids were brought into this process from both the inner and outer solar system. This fact becomes quite important later. Not all asteroids are the same, and you may be familiar with the terms S-type and C-type asteroids. S-type asteroids are the stony asteroids, from the inner solar system, mainly made up from silicate materials and nickel iron. They are drier, since they originate from nearer to the Sun. The most common ones are the C-type asteroids. The chondrite asteroids are among the most ancient bodies in our solar system. They originate from the outer asteroid belts, and they have far greater quantities of something that would go on to be vital to our world, water. And all of these asteroids started falling through the field of space our world was traversing. So, to address my first question of how Earth missed all these asteroids when the moon was continually, apocalyptically bombarded. It did not. The timing of this, so far as our planet concerns, was of utmost importance. By this time, the surface of Earth had cooled to create a more stable crust, what today we recognize as the lithosphere. This balkanized anything above from the immense heat off the magma underneath. The magma close to the surface was far hotter than it is now, at 1,600 degrees Celsius, and far more fluid. The heavier elements, particularly iron, had gravitated to the center core, while the lighter elements and minerals stayed at the surface. When the asteroids descended on the surface, they carried with them an entire set of elements and minerals that would stay as part of this surface layer. It is currently believed that most of the significant deposits that we have on the surface today, ores and metals like lead, nickel, copper, and gold, were deposited there by this process. More crucial than precious metals, though, was the delivery of water. Huge quantities of water. If all of this water had come earlier, when our planet's surface was warmer and less capable of holding an atmosphere, much, or even all of this water would have evaporated back into space, perhaps carrying the planet an empty desert like Mars and the Moon, enveloping Earth at the time of bombarding Terminal 4 billion years ago was a poisonous atmosphere of methane, and ammonia blanketing an unreliable but-folding surface of basalt-type rock, dark gray, nearly black in color, and with vivid liggling lava spilling through faults. Wherite was broken by the impending hailstorm of asteroids. Boiling seas of water were building up, assisting in further cooling the forming surface, a veritable vision of hellfire, brimstone. It is in part due to this turbulent characteristic off-surface, floating on liquid magma, that today's way observe no record of the craters made by these impacts. The creating lithosphere was broken into numerous small tectonic plates that rotated about and cycled themselves much quicker than they do today. And no record of these original rocks persists. The oldest existing rock formations on our Earth approximately date the end of the Hadean era, and by then, this heavy bombardment off our world had most likely ceased. The termination of the Hadean era also signifies the start of a new phase in our world's interesting history, the history of life. It has long been the subject of controversy how the very origin of life might have developed on Earth. The major Building blocks would have been required hydrocarbons and other complex molecules. What circumstances might have given rise to the origins of this molecular organic soup? Interestingly, though, there is controversy regarding the existence of the late heavy bombardment. This theory does assist with answering this critical question. It is now known that all 5 of the essential building blocks of DNA and RNA exist in space and have been found on meteorites. But while the meteorites that we see today burning up in the night sky as they enter our atmosphere could never bring anything as delicate
as these molecules
onto the surface of our world, they would incinerate to nothing before even reaching the stratosphere. But when much larger objects from beyond our world were showering water and icy onto our freshly formed surface, it is very possible that they seeded the Earth with some off-correct ingredients that made life possible. There is strong evidence that life started at the exact moment when this bombardment was being brought to an end, and new oceans had been created. Discovering answers to many of these questions is virtually impossible on Earth, because so little remains from that period. That is why scientists are so eager to research clues that might still be present on the Moon. The reason why this evidence is preserved so well on the Moon is that in contrast to Earth, the surface of our Moon was already very stable without churning and recycling of the surfaces that took place here on our Earth then, so the craters are still intact. Also, the surface off the Moon isn't being constantly worn away by weathering. There are no oceans to wear it down, no acid rain and wind. To strip the rock away, the dust that covers the surface is pulverous cedric, which has never been disturbed since those dramatic impacts billions of years ago. We have craters on the surface of our planet, like the Barringer crater in Arizona, USA, but that is only from 50,000 years ago. Of the late heavy bombardment era craters themselves, there is nothing visible at the present time. If such craters do survive somewhere on our planet, have not been completely eroded away, they could be buried under later sediments or lava flows, and we may never find them. We've been able to make progress in your appreciation of this period due to the remarkable 382 kilograms of rock from the Moon's surface returned to Earth by the Apollo missions. Radiometric dating of rock samples revealed that they had solidified in a very short time, a window of about 3.9 billion years ago, which was in agreement with when we thought that Earth and the rest of the inner planets were getting hit by asteroids. All those big craters on the Moon are where asteroids have hit the surface, and then lava has come flowing out, creating those typical smooth craters which we can observe on clear nights. Not everyone, however, is in agreement, as more sophisticated analytic methods have evolved with the passing of time. Queries have been raised regarding the length of time and timescale of this asteroid active period. Some dating discrepancies indicate that the craters could have been produced over many more years, trailing away from planetary accretion that created the terrestrial planets, instead a far more concentrated period of activity. The sample materials that scientists have available from the Apollo missions are still limited, as they stem from just a few carefully selected locations. More samples from future missions will hopefully resolve some of this controversies, and the NASA Artemis missions could see another landing on the surface off the Moon as early as 2026. I look forward to seeing what new secrets this might reveal. The late heavy bombardment theory is perhaps not an ideal solution, but it is a good story that makes sense, since it fits in with what we have observed about the Moon and about what has been explored so far of our planet's surface, and it offers some potential explanations to the question of how there came to be so much water on the surface of what was once a ball of molten rock. Whether this proves to be the right tale or not, when you next boil the kettle or swim in the ocean, you may be thinking where that water originated and how fortunate the Timingoff. It all had to be in order to actually remain here and form a planet so friendly to life. I will hope that you will be along with me for the next video in this series, when we will delve into another chapter of the amazing history of our lovely blue marble, Earth planet,